James Clerk Maxwell was born on June 13, 1831 in Edinburgh, Scotland, a city renowned for its intellectual energy, scientific curiosity, and cultural dynamism. His arrival into the world coincided with a century of extraordinary change, both in science and in society. Scotland had already given birth to pioneering thinkers such as David Hume and Adam Smith, and in the early 19th century the Scottish Enlightenment was still resonating across Europe. Into this rich intellectual environment came Maxwell, a child who from his earliest years displayed the unmistakable signs of a mind that would one day shape the course of physics forever. His parents, John Clerk Maxwell and Frances Kay, were part of a family that valued education, inquiry, and devotion to personal development. His father, a lawyer by training and a landowner by position, was deeply attentive to his son's upbringing, and his mother, a woman of intelligence and nurturing care, encouraged her young boy's curiosity with patience and warmth. Maxwell's childhood was spent largely at the family estate known as Glenlair in Galloway, a rural region of southwest Scotland. It was here, amid the natural beauty of rolling fields, streams, and open skies, that his first fascinations with the patterns of nature emerged. As a boy, he displayed a kind of insatiable curiosity that his family affectionately referred to as his drive to ask, "What's the go all that?" This phrase, repeated over and over, became symbolic of his restless urge to understand why the world worked as it did. Unlike many children, who might grow bored or distracted, Maxwell's mind seemed endlessly energized by even the smallest details. He would observe the shapes of leaves, the colors of the sky at different times of day, the behavior of animals, and the flow of water, all with a kind of intensity that foreshadowed the scientist he would become. His mother, Frances, recognized early that James possessed a rare mind, one that needed to be nurtured with education as much as affection. She personally undertook much of his early teaching, instilling in him not only reading and writing, but also the basics of arithmetic and an appreciation for poetry and storytelling. She also guided him into the wonders of religious thought and moral instruction, believing strongly that a good education combined intellectual knowledge with spiritual grounding. Tragically, Frances died when James was only 8 years old, leaving a deep absence in his young life. Her death from abdominal cancer meant that his father had to take a more direct role in raising him, but by then her influence was already firmly embedded in James's character. Curiosity, compassion, and discipline became the guiding principles of his life. With his mother gone, James's father sought the best schooling for his son. He first placed him at the Edinburgh Academy, one of the most prestigious schools in the city, where James's talents quickly became apparent. At first, Maxwell struggled socially, partly because of his rural accent, old-fashioned clothing, and unusual mannerisms. His classmates, who came mostly from well-to-do city families, mocked him with nicknames such as Dafty, suggesting that his eccentric curiosity made him appear strange. But despite these early challenges, James quickly proved his brilliance. By the age of 14, he had already won medals for his skills in mathematics, poetry, and classics. His teachers noted that he had a remarkable ability, not simply to memorize lessons, but to see connections between different subjects, to recognize patterns, and to express ideas in creative ways that were unusual for someone so young. One of his earliest scientific achievements came when he was only 15. Fascinated by geometry and by the patterns he noticed in shapes, Maxwell began investigating the properties of curves and ellipses. He discovered a general method for drawing mathematical curves using string, pins, and pencils, creating what would later be called ovals of Cassini, and more complex geometrical shapes. His work was so advanced that it caught the attention of the Royal Society of Edinburgh, Scotland's leading scientific body. At just 15, Maxwell presented his paper on the description of oval curves and those having a plurality of foci, a remarkable achievement that demonstrated his ability to combine playful experimentation with rigorous mathematics. Though the paper was formally read to the society by his professor, Since James was considered too young to present it himself, the accomplishment placed him firmly in the path of intellectual recognition. This was a moment that foreshadowed the way Maxwell's life would blend creativity with discipline, playfulness with precision, and youthful curiosity with scholarly depth. Maxwell's education did not stop with mathematics. At the Edinburgh Academy and later at the University of Edinburgh, he explored Latin, Greek, and philosophy. He developed an appreciation for the arts, poetry, and literature, writing verses of his own that revealed his sensitivity to language and rhythm. Unlike many scientific geniuses who focus narrowly on one domain, Maxwell cultivated a broad intellectual landscape. He believed that understanding the universe required not just mathematics, but also imagination, language, and a sense of beauty. His exposure to classical studies gave him a respect for history and culture, which balanced his natural inclination toward science. At the University of Edinburgh, where he studied from 1847 to 1850, Maxwell encountered some of Scotland's greatest scientific minds. He attended lectures by Sir William Hamilton, the philosopher, and by James Forbes, the physicist known for his studies of heat and glaciers. Here, Maxwell immersed himself in experimental science as well as theoretical study. He became skilled in designing and conducting experiments, often improvising with simple equipment to explore complex ideas. For example, he performed optical experiments to investigate the behavior of light and develop mechanical models to represent mathematical concepts. His approach combined hands-on curiosity with theoretical brilliance, a hallmark of his later career. One of his most important educational steps came when he moved to Cambridge University in 1850. At Cambridge, he entered Peterhouse but soon transferred to Trinity College, where he found the intellectual environment more stimulating. Cambridge was, at the time, the heart of British mathematics, and it was here that Maxwell honed his skills under the rigorous system of mathematical training known as the tripos. This was a famously demanding course of study that tested not only mathematical ability, but also intellectual stamina and endurance. Maxwell thrived in this environment, becoming a Wrangler, a title given to the highest performing mathematics students. Though he did not take the very top spot in his examinations, his teachers and peers recognized that his genius was not easily measured by exams alone. His originality and independence of thought set him apart from the typical brilliant student. While at Cambridge, Maxwell deepened his engagement with electricity, magnetism, and the nature of physical forces. He became friends with some of the leading thinkers of the day and entered into the vibrant scientific debates of the mid-19th century. His education at Cambridge gave him both the tools of advanced mathematics and the community of scholars that would challenge and inspire him. Importantly, it was at Cambridge that Maxwell learned to integrate the abstract power of mathematics with the concrete observations of experimental science. This integration became the foundation of his later revolutionary work in electromagnetism. Even in his student years, Maxwell displayed a distinctive style of thinking. He was not content with simply solving problems. He wanted to understand the deeper principles that tied phenomena together. He approached science with a mixture of humility and confidence, respecting the work of those before him, but daring to ask questions that others had overlooked. His notebooks from this period reveal a mind constantly seeking unity and connection. He would sketch diagrams, write out long chains of equations, and then intersperse them with notes and reflections that revealed his creative process. Maxwell's education was not confined to formal institutions. His upbringing in the Scottish countryside had instilled in him a lifelong love of observation. He would often return to Glenlair during his university years, spending time with his father and continuing his experiments in the quiet of the estate. Here he could observe the play of light in the sky, the movement of water in streams, and the forms of natural objects, all of which inspired his scientific imagination. His education, in this sense, was both academic and personal, both structured and spontaneous. It was the blend of these influences that made Maxwell's mind so original and so powerful. By the time Maxwell completed his studies, he had already established himself as one of the brightest young scientists of his generation. His early life and education had given him a foundation not only of knowledge but of habits of mind, curiosity, rigor, creativity, and a sense of unity in the diversity of nature. These traits would guide him through the rest of his career, enabling him to achieve insights that would transform physics. What makes Maxwell's early years so significant is not just that he was precocious, but that he embodied a way of thinking that valued both precision and imagination, both detail and vision. His childhood questions of, "What's the go o' that?" evolved into some of the most profound inquiries in science. Inquiries that reshaped humanity's understanding of the universe. When Maxwell left the structured environment of Cambridge with the reputation of a prodigy, he was already shaped by the experiences of his early life in ways that would mark him for the rest of his career. To understand the full picture of his formative years, it is important to look not only at his academic achievements, but also at the personal and cultural influences that gave depth to his education. His childhood in rural Scotland had imprinted on him a love for the natural world, and this never left him. Even as he pursued highly abstract mathematics at Cambridge, he carried with him the memory of rivers, hills, and skies, translating their forms into geometry and physics. For Maxwell, the universe was never cold abstraction. It was alive with patterns waiting to be revealed. His intellectual upbringing was deeply shaped by the dual influences of family encouragement and personal resilience. After the loss of his mother, the role of his father was critical. John Clerk Maxwell, though not a scientist himself, gave James the freedom to explore, to experiment, and to make mistakes. He invested in books, provided space for study, and fostered a spirit of inquiry. John's attitude created a balance of discipline and independence. James was expected to work hard, but he was also given the liberty to follow his interests. This balance of structure and freedom became central to Maxwell's way of learning. It gave him the confidence to challenge established ideas while still respecting the rigors of scientific thought. At the Edinburgh Academy, Maxwell's experience as a somewhat isolated student shaped his character. The ridicule he endured in his early years for his accent and clothing might have discouraged a less determined child, but for Maxwell it became a lesson in perseverance. The teasing did not deter him from asking questions or from indulging in his peculiar enthusiasm for geometry and natural philosophy. Instead, it hardened his resolve and taught him to value knowledge over popularity. Over time, his classmates began to respect his brilliance, especially as he consistently excelled in mathematics and science. By the time he left the academy, Maxwell had transformed from a boy mocked for his oddness into a recognized intellectual force. Another key part of Maxwell's education was his early exposure to the scientific community of Edinburgh. The city was a hub of intellectual exchange, with societies, lectures, and debates that encouraged the public discussion of ideas. Through his professors and mentors, Maxwell came into contact with this vibrant environment, which allowed him to present his first paper at the astonishing age of 15. This experience not only validated his abilities, but also gave him confidence in the scientific method of sharing, critiquing, and improving ideas through communal exchange. It also revealed that science was not just a private pursuit, but a collective enterprise, one that depended on dialogue, communication, and collaboration. The transition to the University of Edinburgh marked a period of broad intellectual exploration. Unlike many students who focused narrowly on their chosen discipline, Maxwell took full advantage of the university's offerings. He attended lectures on philosophy, logic, and literature alongside his scientific studies. This broad education shaped his worldview and prevented him from becoming confined to a single perspective. The influence of Sir William Hamilton, for instance, exposed him to philosophical debates about the nature of perception, reality, and the limits of human understanding. While Maxwell would later approach such questions through the lens of physics and mathematics, These early encounters with philosophy encouraged him to think deeply about the relationship between observation and theory, between mind and nature. It was also at Edinburgh that Maxwell began developing a systematic approach to experimentation. With limited resources, he learned to improvise equipment from everyday objects. He designed experiments on polarization of light, studied color vision by mixing pigments, and constructed mechanical models of complex mathematical ideas. This ingenuity would later become a hallmark of his career. Many of his greatest breakthroughs were not the result of expensive laboratories, but of simple yet clever experimental setups guided by brilliant theoretical insight. In this sense, his education was as much practical as it was theoretical, teaching him the value of resourcefulness and creativity in science. When Maxwell moved to Cambridge, the rigor of the Tripos examination system pushed him to the limits of his endurance. The intensity of the mathematical training at Cambridge was legendary, and many students found it overwhelming. For Maxwell, it was an opportunity to sharpen his natural abilities. The Tripos emphasized problem-solving under pressure, requiring students to manipulate equations quickly and accurately. While Maxwell did not rank first in his class, he impressed his instructors with his originality. He often took unconventional approaches to problems, preferring to understand underlying principles rather than merely applying formulas. His examiners sometimes remarked that his answers showed unusual methods, a polite way of acknowledging that Maxwell thought differently. Cambridge also exposed Maxwell to a community of brilliant minds. He participated in intellectual societies, attended debates, and made friendships that enriched his scientific life. The conversations and exchanges he had during this period widened his perspective and reinforced his commitment to science as a shared human endeavor. Unlike the solitary genius stereotype often attached to scientists, Maxwell thrived in dialogue. He enjoyed discussing ideas, debating principles, and refining his theories in conversation with others. His education was therefore deeply social as well as individual, shaped by the interactions and challenges of his peers. The young Maxwell's character combined humility with quiet confidence. Despite his extraordinary abilities, he did not adopt arrogance or superiority. He often displayed a gentle humor and a willingness to listen to others, qualities that made him approachable. This humility, however, coexisted with a deep certainty in the power of science to uncover truth. He was unshaken in his belief that mathematics could reveal the hidden structures of the universe, and this conviction guided him throughout his career. His early education reinforced this faith, showing him again and again that persistent inquiry yielded clarity, that patterns could be found even in apparent chaos. Another significant element of Maxwell's formative years was his relationship with faith and spirituality. Raised in a religious household, he absorbed a sense of the universe as an ordered creation. For Maxwell, science and faith were not in conflict but in harmony. His education included the study of scripture alongside the study of mathematics, and he regarded both as ways of seeking truth. While later generations would often struggle with the perceived opposition of science and religion, Maxwell himself found inspiration in the belief that the natural world reflected deeper principles of order and design. This integration of spiritual and scientific perspectives gave his work a sense of purpose and wonder. As Maxwell's education came to a close, it became clear that he was not just a talented student, but a thinker prepared to challenge the boundaries of knowledge. His early experiences had cultivated a habit of seeing unity in diversity, of connecting disciplines that others kept apart. From his geometrical experiments as a teenager to his broad philosophical studies at university, Maxwell was preparing himself, perhaps unconsciously, for the great task of unifying electricity, magnetism, and light. The seeds of his later genius were already planted in his early years, nourished by family support, rigorous schooling, exposure to intellectual debate, and his own boundless curiosity. Reflecting on Maxwell's early life and education, one cannot help but notice how each experience added a layer to his character and intellect. The rural freedom of Glenlair gave him imagination. The loss of his mother taught him resilience. The discipline of the Edinburgh Academy gave him rigor. The intellectual climate of Edinburgh gave him opportunity. The broad studies at university gave him perspective, and the challenges of Cambridge gave him precision. Together, these influences forged a mind capable of reshaping physics. By the time Maxwell entered the world as a professional scientist, he carried within him the lessons of a lifetime of learning. His early life was not merely preparation, but a microcosm of the principles he would later embody in his work: curiosity that refuses to stop asking questions, discipline that insists on rigor, imagination that sees beyond the obvious, and humility that recognizes the beauty of truth wherever it may be found. His education was more than a series of institutions. It was a journey of the mind and spirit, one that equipped him to become not only a great scientist, but a visionary capable of seeing the hidden unity of nature. The story of James Clerk Maxwell's early years is therefore not simply a biography of a young prodigy, but a reminder of how greatness is nurtured. It is shaped by family, by environment, by personal struggle, and by the willingness to pursue knowledge with both seriousness and joy. Maxwell's life from childhood to the end of his education is a testament to the power of curiosity and the importance of providing space for that curiosity to grow. Long before he wrote the equations that would change the world, he was already practicing the art of unification, bringing together observation and theory, science and philosophy, discipline and creativity. These lessons, deeply embedded in his character, were the true foundation of his later achievements. James Clerk Maxwell's fascination with mathematics and natural philosophy was not a passing interest, but the central thread of his life, woven into his thoughts and actions from childhood to his earliest work as a scholar. For Maxwell, mathematics was never simply a discipline of numbers and symbols, nor was natural philosophy merely the study of phenomena. Together they were a language and a worldview, a means by which the hidden architecture of the universe could be revealed. This passion can be traced back to his youth, when the beauty of patterns in nature stirred in him questions that could only be answered by turning curiosity into inquiry, and inquiry into disciplined thought. As a child, Maxwell was enthralled not just by how things appeared, but by why they behaved as they did. He did not look at the ripples of a pond as idle play of water. He wanted to understand the geometry of their expansion. He did not marvel at the colors of a butterfly merely for their charm. He asked what rules governed their combinations. For a boy of his temperament, mathematics was not an abstract burden but a tool, an instrument for decoding mysteries. He instinctively saw the world in terms of form, relation, and law, and mathematics gave him the framework to express what he intuited. When he entered the Edinburgh Academy, his gift for geometry and algebra became evident. While other students struggled with the rigidity of Euclidean constructions, Maxwell treated geometry as a living language. He filled his notebooks with sketches of curves and diagrams, finding joy in the clarity and precision that mathematics offered. One of his earliest triumphs, the discovery of methods to construct ovals and related curves using simple tools, was a vivid example of this marriage of curiosity and formal reasoning. What for others might have been a playful, drawing exercise became for Maxwell a step into the deeper order of mathematics, a glimpse into the way geometry mirrored the patterns of the natural world. But Maxwell's relationship with mathematics was not a dry affair of memorization and calculation. He brought to it imagination and even playfulness. He could translate problems into visual pictures, and he often thought in terms of mechanical analogies, representing abstract equations with physical models. This approach allowed him to handle complexity without losing the intuitive sense of meaning behind the symbols. Mathematics, for him, was not a set of rules but a form of art, a bridge between imagination and reality. Natural philosophy, which in Maxwell's time was the term for what we now call physics, was the natural partner of his mathematical inclination. He was drawn irresistibly to questions about forces, fields, and the fundamental workings of nature. At the University of Edinburgh, and later at Cambridge, he was captivated by the experiments of his professors and the debates of the scientific community. He studied optics, electricity, and magnetism, and in each case sought not only to observe phenomena, but to describe them with mathematical precision. His goal was always to find the unity beneath the diversity, the hidden law that explained the apparent chaos. What is striking about Maxwell's early engagement with mathematics and natural philosophy is the depth of his vision. He was not content with the immediate results of calculation or experiment. He wanted to understand the principles that connected different domains of science. For example, in his teenage years, he did not limit himself to geometry alone. He explored the relationship between geometry, light, and perception, anticipating later work in optics and color theory. He already displayed the habit of moving across boundaries, blending mathematics, physics, and even psychology in his search for truth. At Cambridge, this fascination matured into a disciplined practice. The Tripos examinations required not only mechanical skill, but also creativity in solving difficult problems, and Maxwell thrived in this environment. He could take a mathematical expression and imagine the physical situation it described, or conversely, he could look at a physical experiment and derive the equations that must govern it. This dual ability made him stand out from his contemporaries. Mathematics for him was never divorced from reality. It was the grammar of nature, a precise yet elegant way to articulate the laws of the universe. Maxwell's notebooks and writings from this period show the joy he found in discovery. He wrote equations alongside reflections, diagrams alongside poetic phrases, blending logic with imagination. For him, the work of the mind was not confined to one register, but spanned the whole range of human thought. This holistic approach to mathematics and natural philosophy is one of the reasons his contributions later had such far-reaching effects. He was not simply calculating but envisioning, not merely proving but revealing. Even in his early explorations, Maxwell sensed that mathematics could do more than describe, it could predict. This conviction was strengthened as he studied the works of predecessors like Newton, Fourier, and Faraday. Newton had shown how mathematics could govern motion, Fourier had revealed the hidden harmonies of heat and vibration, and Faraday had demonstrated the mysterious patterns of electrical and magnetic forces. Maxwell absorbed these influences, but was not content to merely admire them. He felt compelled to extend them, to find the next step in the unfolding story of science. This drive was evident in his fascination with electricity and magnetism. Faraday's experiments had shown patterns in fields of force, lines that seemed to obey invisible laws. Maxwell was captivated by these ideas, and his mathematical instinct urged him to give them form. He realized that the language of mathematics could capture what Faraday had seen with his experimental eye, turning descriptive observations into precise equations. Here again, his twin fascinations, mathematics and natural philosophy, came together in perfect harmony. But Maxwell's passion for natural philosophy was not limited to forces and fields. He explored the properties of gases, seeking to understand the laws governing their motion and distribution. He investigated optics, studying how light behaved and how colors combined. He examined the theory of stability in rotating bodies, exploring principles that would later inform engineering and astronomy. In each case, his approach was the same: to probe phenomena with curiosity, to model them with mathematics, and to search for unity beneath diversity. His broad interests might have seemed unfocused to some, but they were in fact manifestations of a consistent vision. Maxwell believed that the universe was not a collection of unrelated parts, but a coherent whole. Mathematics and natural philosophy were his tools for uncovering that coherence. His fascination was not in the details alone, but in the patterns that connected the details. Whether he was studying light, electricity, gases, or geometry, he was always guided by the same instinct: to see the invisible order that lay beneath. What made Maxwell's fascination so enduring was that it was fueled not only by intellectual drive, but also by aesthetic appreciation. He found beauty in equations, elegance in the simplicity of laws, harmony in the unity of forces. For him, science was not just useful but profoundly meaningful, a form of art that reflected the underlying beauty of creation. His writings often reveal this sense of wonder, this joy in discovery. It was as if he saw in mathematics and natural philosophy not just knowledge but a kind of poetry, a music of the spheres expressed in symbols and laws. In these formative years, Maxwell was laying the foundation for the breakthroughs that would later transform science. His fascination with mathematics and natural philosophy was not an idle pursuit, but a lifelong vocation, a devotion to truth that guided every step of his career. By the time he completed his education, he had already demonstrated the qualities that would make him a scientific giant: the ability to combine observation and theory, the vision to see unity where others saw separation, and the passion to pursue knowledge not only with rigor but with joy. As Maxwell matured as a scholar, his fascination with mathematics and natural philosophy deepened into a philosophy of inquiry, a belief that mathematics was not merely a discipline to be studied, but a key to unlocking the mysteries of the cosmos. This conviction became clearer during his time at Cambridge, where his mind expanded under the influence of the rigorous mathematical culture and the vibrant debates in natural philosophy that surrounded him. It was here that he learned not just the techniques of calculation, but the spirit of discovery, the confidence that abstract symbols on a page could describe and predict the behavior of the physical world. Among his peers and mentors, Maxwell was recognized not simply as a diligent student, but as a thinker who saw beyond the obvious. Many of his fellow students approached mathematics as a competitive exercise, mastering problems for the sake of examinations. Maxwell, though equally capable of excelling under these pressures, treated mathematics as something far more profound. To him, equations were not sterile manipulations, but living expressions of truth. Each formula carried meaning, each theorem revealed a hidden structure. His notebooks were filled not only with calculations but with sketches and analogies, reflections and questions that displayed his unusual way of thinking. It was during these years that Maxwell encountered the work of Michael Faraday, whose experimental investigations into electricity and magnetism had revolutionized science. Faraday, however, had little formal training in mathematics, and his descriptions of fields and forces were often qualitative, expressed through visual imagery rather than equations. To Maxwell, this was both an inspiration and a challenge. He admired Faraday's vision, but felt compelled to translate it into the precise language of mathematics. Here his twin fascinations, mathematics and natural philosophy, found their perfect meeting point. The experimental insights of Faraday became for Maxwell the raw material for a grand synthesis, one that mathematics could refine into universal laws. This habit of bridging experiment and theory was characteristic of Maxwell's approach to all of natural philosophy. He did not regard mathematics as detached from reality, nor did he view experimental science as sufficient without theory. Instead, he saw them as two sides of the same coin, each incomplete without the other. His fascination lay in the interplay between them, the way abstract reasoning could illuminate experiment, and the way observation could guide and inspire mathematical models. This balance would later enable him to formulate the famous equations that unified electricity and magnetism. But the roots of this achievement can be traced to his early fascination with both domains. Maxwell's intellectual journey also included a strong engagement with the history of natural philosophy. He was well read in the works of Newton, who had demonstrated the power of mathematics to govern the motion of planets and projectiles alike. Newton's example confirmed for Maxwell that mathematics could unify seemingly disparate phenomena under a single set of laws. He also studied the contributions of Fourier, whose analysis of heat flow introduced him to the concept of representing complex patterns through mathematical series. These influences shaped Maxwell's understanding of mathematics not as a static body of knowledge, but as an evolving language, capable of expanding to describe new realities. Beyond physics, Maxwell was intrigued by the philosophical questions underlying mathematics and natural philosophy. He wondered about the relationship between the human mind and the external world, about whether mathematics was discovered or invented, about how abstract reasoning could capture truths about nature. These reflections gave depth to his fascination, making it not merely a technical pursuit, but an exploration of fundamental questions. To him, mathematics was a dialogue between the human mind and the order of creation, a conversation in which symbols and equations revealed truths that were both universal and eternal. The scope of Maxwell's interests during this period was remarkably broad. He studied color vision, exploring how the human eye perceives light through the combination of three primary sensitivities. Here again, mathematics played a crucial role, allowing him to design experiments and interpret results in a precise way. He constructed a color top, a simple device with spinning disks of different colors, to test his theories and confirm that color perception could be described mathematically. What fascinated him was not only the phenomenon itself, but the way mathematics could capture the subtleties of perception, turning subjective experience into measurable law. He also explored the kinetic theory of gases, where he applied probability and statistics to the behavior of molecules in motion. This was a bold move at a time when many physicists resisted the idea of using statistical reasoning in physics. Maxwell, however, saw that mathematics could reveal patterns even in randomness, that the apparent disorder of molecules could still obey laws when considered in large numbers. This insight, too, sprang from his fascination with the power of mathematics to extend beyond the obvious, to capture hidden order beneath apparent chaos. In every domain he touched, Maxwell displayed the same qualities: curiosity that refused to rest with surface explanations, imagination that sought patterns and connections, and discipline that expressed these insights in rigorous mathematical form. His fascination with mathematics and natural philosophy was not narrow or specialized but expansive, encompassing the full range of physical phenomena and beyond. He treated mathematics as a universal key, capable of unlocking the secrets of light and color, of electricity and magnetism, of gases and heat. What made Maxwell's fascination extraordinary was the joy that infused it. He approached science not with grim determination, but with delight, as if each problem were a puzzle waiting to be solved, each phenomenon a clue to a larger mystery. His writings and letters often reveal this sense of play, this lightness of spirit that made his work not a burden but a source of happiness. It was this joy, perhaps, that sustained him through the challenges of his career, allowing him to persist in difficult problems and to embrace the long labor of discovery. By the time Maxwell completed his formal education, his fascination with mathematics and natural philosophy had become more than personal enthusiasm. It had crystallized into a way of life. He had learned to see mathematics not as an end in itself, but as a bridge to understanding nature, and he had learned to see natural philosophy not as a collection of observations, but as a realm of laws waiting to be revealed through mathematics. This integration of thought defined his intellectual identity and prepared him for the revolutionary contributions that would follow. Looking back on Maxwell's early years, one can see how this fascination shaped not only his career, but the trajectory of science itself. His vision of mathematics as the language of natural philosophy inspired him to unify electricity, magnetism, and light, to predict phenomena that would later transform technology, and to provide a foundation for modern physics. His story reminds us that science is not driven by technique alone, but by fascination, by the deep curiosity and wonder that make the human mind seek understanding in the first place. In Maxwell's case, this fascination with mathematics and natural philosophy was the wellspring of genius, the source of insights that changed the world. The story of James Clerk Maxwell's development of the equations that unified electricity and magnetism is one of the most remarkable chapters in the history of science. To appreciate its magnitude, One must remember the state of knowledge before Maxwell entered the scene. In the early 19th century, electricity and magnetism were known phenomena, studied with great interest, but treated as distinct forces of nature. Electricity was associated with sparks, shocks, and batteries, while magnetism was linked with lodestones and compasses. Experiments by men like Alessandro Volta, André Marie Ampère, and Michael Faraday had revealed fascinating connections between these phenomena, but the underlying unity remained hidden. Into this landscape stepped Maxwell, bringing with him the rare combination of deep mathematical skill and a visionary imagination capable of seeing what others could not. The seeds of Maxwell's unification were planted in his early encounters with the work of Michael Faraday. Faraday, though lacking advanced mathematical training, had an extraordinary experimental genius. Through careful and ingenious experiments, he had shown that electricity could generate magnetism, and that magnetism could induce electricity. He conceived of invisible lines of force that spread out from magnets and electric currents, filling space with patterns of influence. These lines of force were not just metaphors to Faraday, they were real entities, a way of understanding how forces acted across space. For many in the scientific community, Faraday's descriptions were too qualitative, too vague, but to Maxwell they were a revelation. He saw in Faraday's ideas the basis of a new mathematical vision, one that could unify the diverse phenomena of electricity and magnetism into a coherent whole. Maxwell's genius lay in translating Faraday's physical intuition into mathematics. Where Faraday had seen lines of force, Maxwell saw fields, continuous regions of space where every point was associated with a vector describing the strength and direction of force. This concept of the electromagnetic field was revolutionary. Instead of thinking of forces acting instantaneously at a distance, as Newtonian physics had often done, Maxwell conceived of forces as transmitted through space by fields. This shift in perspective transformed the way scientists would think about nature. The challenge for Maxwell was to express this vision in precise mathematical form. Beginning in the 1850s, he embarked on a series of investigations that would culminate in the formulation of the equations that now bear his name. His first major step came in 1856 when he wrote his groundbreaking paper on Faraday's lines of force. In this work, Maxwell attempted to give a mathematical description of Faraday's experimental observations. He introduced mechanical analogies, imagining space filled with tiny vortices and idle wheels, whose interactions represented the behavior of electric and magnetic fields. Though these mechanical models would later be discarded, they were crucial stepping stones for Maxwell. They provided him with a way of visualizing abstract relationships, allowing him to develop the mathematics that captured the essence of electromagnetic phenomena. Over the next decade, Maxwell refined his ideas, drawing together the results of experiments from across Europe and uniting them within a single mathematical framework. He recognized that the laws governing electricity, as formulated by Gauss, Ampère, and others, could be integrated with the laws of magnetism and Faraday's law of induction. But there was a problem. The equations as they stood were incomplete. Ampère's law, for example, described how electric currents produce magnetic fields, but it failed to account for situations where electric charge accumulated, as in a charging capacitor. Maxwell saw the gap and provided the missing term, which he called the displacement current. This was not a current of moving charges, but a changing electric field that could act like a current in generating magnetic effects. By introducing this concept, Maxwell completed the symmetry between electricity and magnetism, ensuring that the equations were consistent in all situations. This insight was more than a correction, it was a stroke of genius. The displacement current not only solved the mathematical inconsistency, but also led directly to the prediction of electromagnetic waves. Maxwell's equations implied that a changing electric field could produce a magnetic field, and a changing magnetic field could produce an electric field. These two effects together meant that disturbances could propagate through space as sustaining waves of electricity and magnetism. Calculating the speed of these waves from his equations, Maxwell found that it matched the measured speed of light. In a moment of profound realization, he concluded that light itself was an electromagnetic wave. This was one of the most astonishing discoveries in the history of physics. For centuries, light had been a mystery, debated as either a particle or a wave, its nature elusive and puzzling. Maxwell revealed that light was not separate from electricity and magnetism, but part of the same fundamental phenomenon. The glow of a candle, the colors of the rainbow, the invisible waves that later became radio, all of these were manifestations of electromagnetic fields. Maxwell's equations had united what had once seemed like separate domains into a single framework, demonstrating the unity of nature with breathtaking clarity. The four equations that emerged from Maxwell's work are elegant and concise, yet their implications are immense. They describe how electric charges produce electric fields, how currents produce magnetic fields, how changing magnetic fields induce electric fields, and how electric and magnetic fields sustain each other in waves. These equations are not just rules but universal laws, governing phenomena from the smallest scales of atoms to the vast reaches of space. They embody the unity of physics in a way that few other scientific achievements have done. Maxwell published his comprehensive theory in 1865 in his paper, A Dynamical Theory of the Electromagnetic Field. This was the culmination of years of thought, calculation, and refinement. In it, he laid out the equations in their mature form and presented the extraordinary conclusion that light is an electromagnetic wave. The scientific community at first struggled to grasp the significance of his work. Many physicists of the time were still wedded to mechanical models and found it difficult to accept the abstract notion of fields as real physical entities. Yet slowly, as experiments confirmed Maxwell's predictions, the power of his theory became undeniable. The development of Maxwell's equations was not just a triumph of mathematics, but a testament to his philosophical vision. He believed in the unity of nature, in the idea that diverse phenomena could be explained by a small set of principles. His equations gave expression to this belief, showing that electricity, magnetism, and light were not separate forces, but different aspects of the same reality. This unification was not only intellectually satisfying, but also profoundly beautiful, a harmony of mathematics and natural philosophy that reflected Maxwell's deepest passions. What made Maxwell's achievement even more remarkable was that it opened the door to discoveries he could scarcely have imagined. His equations predicted the existence of electromagnetic waves beyond the visible spectrum, and later scientists like Heinrich Hertz would confirm this by generating and detecting radio waves. From this foundation arose the technologies of radio, television, radar, and modern communications, transforming human society. Maxwell's unification thus stands as a perfect example of how pure scientific curiosity can lead to practical revolutions, how the fascination with mathematics and natural philosophy can change the world. In his lifetime, Maxwell was modest about his achievement. He did not trumpet his equations as a grand unification, but presented them with the quiet confidence of a man who trusted in the power of mathematics to reveal truth. Yet the magnitude of his work was recognized by the greatest minds who followed him. Albert Einstein would later say that the work of James Clerk Maxwell was the most profound and fruitful that physics had experienced since the time of Newton. Indeed, Einstein's own theory of relativity built directly on Maxwell's field equations, showing how they were consistent with the constancy of the speed of light and the unity of space and time. By the end of his career, Maxwell's equations had become the cornerstone of modern physics, their elegance admired and their power unquestioned. But the path to this achievement was not straightforward. It required not only mathematical brilliance, but also a willingness to see beyond established categories, to trust intuition as well as calculation, and to imagine possibilities that others had not considered. It required the fusion of Faraday's experimental vision with Maxwell's mathematical genius, a collaboration across time and method that produced one of the greatest syntheses in science. The development of Maxwell's equations was, in a sense, the culmination of his lifelong fascination with patterns, unity, and beauty. From the ovals he drew as a child to the fields he described as a scientist, his journey was always about finding connections. His equations were not just tools of physics, but expressions of a worldview, a belief that the universe was coherent, intelligible, and filled with order. They stand today as a monument to that belief, a set of symbols that continue to inspire scientists and thinkers around the world. The years following Maxwell's publication of his dynamical theory of the electromagnetic field were critical in shaping the reception and eventual triumph of his ideas. At first the response was muted. His 1865 paper was dense, mathematically challenging, and written in a style that required both imagination and perseverance from its readers. Many physicists were accustomed to dealing with tangible experiments, mechanical explanations, or direct measurements, and Maxwell's field theory seemed to them a mixture of abstractions and analogies. The notion of displacement current, in particular, appeared obscure as it did not correspond to anything easily observed in the laboratory. Yet Maxwell persisted, refining his ideas, explaining them in different contexts, and patiently waiting for the scientific community to catch up. Part of the difficulty lay in the shift that Maxwell's theory demanded in how scientists conceived of physical reality. For centuries, the dominant model had been action at a distance, the belief that forces like gravity or magnetism acted instantaneously across space without any intervening medium. Newton himself had described gravity in this way, though even he admitted discomfort at the idea of one body acting on another without mediation. Maxwell, building on Faraday, proposed that forces did not act across empty space, but were transmitted by fields that filled space continuously. This concept was not immediately intuitive. It required scientists to think of space itself as active, structured, and dynamic, rather than as a void where objects interacted mysteriously across distance. To aid this conceptual leap, Maxwell often resorted to mechanical analogies. He imagined gears, vortices, and elastic media that could transmit stresses and motions, serving as stand-ins for the invisible fields he was describing. These analogies, though not literally true, provided him with a way to derive equations and to reassure himself that his theory had some grounding in physical intuition. In time, these mechanical models were discarded, but the mathematics they generated endured. This ability to use analogy as scaffolding, then discard it once the structure was built, was one of Maxwell's greatest strengths. As his theory matured, Maxwell realized that the equations he had developed could be expressed in a more compact and elegant form. In his treatise on electricity and magnetism, published in 1873, he presented the equations in a systematic way that allowed later generations to see their true power. Though his original formulation contained 20 equations in 20 variables, later mathematicians such as Oliver Heaviside, Heinrich Hertz, and Josiah Willard Gibbs would refine them into the 4 familiar equations that bear Maxwell's name today. These 4 equations, expressed in vector calculus, became the cornerstone of classical electromagnetism, a model of clarity and universality. The treatise was more than a textbook, it was a manifesto of a new way of doing physics. In it, Maxwell laid out the principles of field theory, developed mathematical techniques for analyzing electromagnetic phenomena, and offered predictions that would inspire experimental tests. Among its most remarkable features was Maxwell's clear statement that light is an electromagnetic wave, a unification that remains one of the most profound in science. Yet even then, the experimental confirmation of this idea lay in the future. Maxwell did not live to see Hertz's generation of radio waves in the 1880s, which would finally vindicate his predictions. His premature death in 1879, at the age of 48, deprived the world of the chance to see him witness the flowering of his ideas. The displacement current, often overlooked by his contemporaries, turned out to be the crucial link in the chain of unification. Without it, Ampere's law was incomplete, failing to satisfy the principle of continuity in the flow of electric charge. With it, the equations became self-consistent and symmetric, allowing the possibility of wave propagation. The elegance of this insight was matched by its depth, for it showed that a purely mathematical correction could reveal new physical realities. This was a profound shift in science. No longer were equations simply tools for describing experiments, they could also predict phenomena not yet observed. Maxwell's work thus laid the foundation for the predictive power of theoretical physics in the modern age. The idea that light was an electromagnetic wave not only unified two great fields of physics, but also expanded the boundaries of what could be imagined. If visible light was electromagnetic, then there might exist other forms of electromagnetic radiation, unseen by the eye but equally real. This prediction, implicit in Maxwell's equations, opened a vast spectrum of possibilities. Indeed, subsequent discoveries confirmed the existence of radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays, revealing that the universe was filled with radiation spanning an enormous range of wavelengths. All of this was contained, in seed form, within Maxwell's equations. Maxwell's unification of electricity and magnetism can be seen as part of a larger pattern in the history of science. The drive to simplify, to reveal underlying connections, to show that what appear to be separate phenomena are in fact aspects of a deeper whole. In this sense, Maxwell was the successor to Newton, who had shown that the motion of the planets and the fall of an apple were governed by the same law of gravitation. Maxwell's achievement was of equal magnitude, for he showed that electricity, magnetism, and light were governed by the same set of equations. Later, Einstein would extend this tradition by uniting space and time, mass and energy, and eventually the electromagnetic field with the geometry of spacetime. But without Maxwell, the path to relativity and modern physics would have been inconceivable. The impact of Maxwell's equations extended far beyond the scientific community. They laid the groundwork for the technologies that would transform human society in the 20th century. The generation of electromagnetic waves, their transmission through space, and their reception at distant points became the basis for radio, telegraphy, television, radar, and modern wireless communications. The entire infrastructure of the information age, from mobile phones to satellites, rests ultimately on Maxwell's insight that changing electric and magnetic fields propagate as waves at the speed of light. The unification he achieved in the 19th century continues to shape daily life in the 21st. Maxwell's role in this revolution is all the more striking when one considers the tools at his disposal. He worked without modern laboratories, without electronic instrumentation, and without the benefit of the powerful computers that later scientists would use to simulate and analyze complex systems. His tools were pen and paper, his resources the accumulated results of earlier experiments, his laboratory the quiet of his study. Out of these modest materials he built a framework that continues to govern physics today. This was a triumph not only of intellect, but of imagination, a testament to what the human mind can achieve when guided by curiosity and discipline. Despite the transformative power of his equations, Maxwell himself remained humble and even playful in his approach to science. He delighted in puzzles, jokes, and poetry, often lightening the gravity of his work with humor. Yet behind this genial personality lay a seriousness of purpose, a dedication to truth, and a conviction that beauty and simplicity were signs of deeper reality. His equations embody this conviction, combining elegance with explanatory power, symmetry with utility. They are not only correct but beautiful, and it is this beauty that has inspired generations of scientists. The legacy of Maxwell's equations is not limited to electromagnetism. They have become a model for what a successful physical theory should be: mathematically elegant, experimentally grounded, and capable of unification. They demonstrated that fields, not just particles, are fundamental to understanding nature. They provided the starting point for quantum theory, as physicists in the early 20th century grappled with the interaction of electromagnetic radiation and matter. They anticipated the notion of gauge symmetry, a concept that now lies at the heart of modern particle physics. In many ways, Maxwell was not only a unifier of electricity and magnetism, but also a prophet of the field-based, unified theories that dominate physics today. Looking back, it is hard to imagine the intellectual leap required to move from the scattered laws of electricity and magnetism to the unified field equations that bear Maxwell's name. Each step of the way demanded courage, the courage to challenge existing assumptions, to introduce new concepts like displacement current, to trust mathematics even when experiments had not yet confirmed the predictions. Maxwell's courage was rooted in his deep fascination with both mathematics and natural philosophy, his conviction that the universe was rational and intelligible, and his willingness to pursue truth wherever it led. By the time of his death, Maxwell had not lived long enough to see the full flowering of his theory, but his work had already begun to reshape the landscape of science. The younger generation of physicists, inspired by his treatise, carried forward his ideas, refining, testing, and applying them. Within a few decades, experiments confirmed the existence of electromagnetic waves, and the age of wireless communication was born. The name of Maxwell, once little known outside the scientific community, became synonymous with the unity of electricity and magnetism, a visionary who had revealed the hidden harmony of the physical world. The unification achieved by Maxwell remains one of the great monuments of human thought. It demonstrates the power of mathematics to reveal truths beyond immediate experience, the value of imagination in guiding discovery, and the enduring quest to find unity in the diversity of nature. His equations continue to govern the design of circuits, the transmission of signals, the propagation of waves, and the behavior of light. They remain as valid today as when they were first written, a testament to the timelessness of fundamental scientific truth. In reflecting on the development of Maxwell's equations, one cannot help but be struck by the way they embody the spirit of science itself. They arose from the careful study of experiments, the bold use of imagination, the disciplined application of mathematics, and the philosophical conviction that nature is unified. They remind us that science is not merely the accumulation of facts, but the search for patterns, the quest for understanding, the drive to see beneath the surface to the deeper laws that govern reality. Maxwell's life and work exemplify this spirit, and his equations stand as its enduring symbol. When most people remember James Clerk Maxwell, they think of the grand unification of electricity and magnetism, the four equations that changed the course of physics forever. Yet his intellectual curiosity and genius were far too wide, ranging to be confined to a single domain. Long before his field equations had reshaped science, Maxwell was venturing into other territories of natural philosophy, bringing the same blend of imagination, mathematical insight, and experimental ingenuity to problems as diverse as the behavior of gases and the nature of human color vision. These contributions, though sometimes overshadowed by his crowning achievement in electromagnetism, were themselves groundbreaking and deeply influential, leaving marks on science that endure to this day. One of Maxwell's earliest triumphs beyond electromagnetism was his work on the kinetic theory of gases. In the mid-19th century, scientists debated the nature of heat and temperature, with some still clinging to the old caloric theory that treated heat as a kind of fluid. Others began to consider that heat might be the motion of particles, a view supported by Daniel Bernoulli a century earlier, but not fully developed. Maxwell, fascinated by the possibilities of mathematics applied to nature, saw that the laws of probability could be a key to understanding gases. He reasoned that if gases were made of vast numbers of molecules in constant motion, colliding and ricocheting like billiard balls, then their collective behavior could be described statistically, even if the exact path of a single molecule could never be known. In 1860, Maxwell published his famous paper, On the Dynamical Theory of Gases, in which he introduced the concept of a distribution of molecular speeds. His result, now called the Maxwell-Boltzmann distribution after Ludwig Boltzmann's later refinements, revealed that not all molecules in a gas move at the same speed, but instead follow a predictable statistical spread. Some move slowly, some very quickly, but most cluster around a certain average. This was a profound insight, for it showed that the macroscopic properties of gases, pressure, temperature, diffusion, could be explained by the microscopic motions of molecules, governed by probability. It was the beginning of statistical mechanics, a field that would become one of the central pillars of modern physics. Maxwell's work on gases also extended to viscosity, diffusion, and thermal conductivity. He predicted that the viscosity of a gas would be independent of its density, a counterintuitive result that was later confirmed experimentally. This prediction not only demonstrated the power of his statistical approach, but also helped persuade skeptics that the molecular theory of matter was correct. In an era when atoms and molecules were not universally accepted as real, Maxwell's calculations gave strong support to the atomic hypothesis. His vision helped transform the understanding of heat from a mysterious fluid into a manifestation of molecular motion, laying the groundwork for thermodynamics and later quantum theory. Even as he was unraveling the mysteries of invisible molecules, Maxwell turned his attention to something as immediate and visible as color. The question of how humans perceive color had intrigued philosophers and scientists for centuries. Isaac Newton had shown that white light could be split into a spectrum of colors, but the mechanisms of perception remained unclear. Maxwell approached the problem with the same curiosity and experimental flair that characterized all his work. Inspired by the earlier theories of Thomas Young and Hermann von Helmholtz, he explored the idea that the human eye perceives color through the action of three types of receptors, each sensitive to a different range of wavelengths. To test this theory, Maxwell conducted experiments using rotating color discs, where segments painted in different hues blended into a single perceived color when spun rapidly. By adjusting the proportions of red, green, and blue on the discs, he demonstrated that any color could be reproduced, supporting the three-color theory of vision. In 1861, Maxwell made history when he applied his research to photography. Working with the photographer Thomas Sutton, he created the first color photograph, an image of a tartan ribbon. The method was simple yet ingenious. 3 separate black and white photographs were taken through red, green, and blue filters, and then projected together using the same filters. When superimposed, the images recreated the original colors of the ribbon. Though the process was imperfect, due to the limitations of photographic materials at the time, the principle was revolutionary. Maxwell had demonstrated not only the validity of the three-color theory, but also laid the foundation for modern color reproduction. From color photography to digital screens, every television, computer monitor, and smartphone that uses red, green, and blue pixels traces its lineage back to Maxwell's pioneering experiments. Maxwell's interests reached even further. He investigated the stability of Saturn's rings, addressing a problem that had puzzled astronomers since Galileo. Were the rings solid, liquid, or made of many small particles? Using mathematics and physical reasoning, Maxwell showed in 1859 that the rings could not be solid or fluid without breaking apart. Instead, they must be composed of countless small particles orbiting independently, a conclusion spectacularly confirmed more than a century later by spacecraft visiting Saturn. In this case, his capacity to combine observation, mathematics, and imagination solved a cosmic riddle long before technology could provide direct evidence. What links these diverse contributions? The kinetic theory of gases, the study of color vision, the analysis of Saturn's rings, is Maxwell's unique way of thinking. He was never content with surface appearances or isolated facts. He sought the deeper structures, the hidden laws, the unity behind diversity. His mathematics was not dry calculation, but a living tool for uncovering patterns in nature. His experiments were not routine demonstrations, but creative acts designed to probe fundamental truths. Whether he was predicting the speed distribution of molecules or projecting the first color photograph, he brought the same spirit of curiosity, rigor, and wonder. Though overshadowed by his unification of electricity and magnetism, these contributions demonstrate that Maxwell's genius was not confined to a single breakthrough. He reshaped entire fields of knowledge, left practical legacies that still touch daily life, and anticipated discoveries that would only be confirmed generations later. His work on gases laid the foundation for statistical physics, essential to chemistry, thermodynamics, and quantum theory. His work on color vision underlies modern imaging and display technologies. His analysis of Saturn's rings revealed the power of mathematics to reach across astronomical distances. Together, these achievements paint a picture of a scientist whose mind was restless, wide-ranging, and profoundly creative. Maxwell did not see barriers between disciplines, but approached all of nature as a unified whole, waiting to be understood. Just as his equations of electromagnetism revealed the deep connection between electricity, magnetism, and light, so too did his explorations beyond that field reveal the interconnectedness of the physical world. In every endeavor, he combined precision with imagination, analysis with intuition, calculation with vision. His legacy is not only the unification of forces, but also the demonstration of how a single mind, guided by curiosity and discipline, can illuminate so many corners of the universe. James Clerk Maxwell is remembered first as a towering figure in theoretical physics, the man whose equations revealed the unity of electricity, magnetism, and light. Yet an equally important part of his legacy lies in his role as a teacher and communicator of science. He was not a solitary genius who locked himself away from the world, but a man who valued dialogue, explanation, and the sharing of ideas. Throughout his career, in the lecture halls of Aberdeen, London, and Cambridge, and in his writings, both technical and popular, Maxwell demonstrated a rare gift for making science accessible while remaining faithful to its depth and rigor. His impact as a teacher extended beyond the classroom to shape the very culture of scientific inquiry in the 19th century. From his earliest days as a student, Maxwell had a love for teaching. He enjoyed explaining concepts to his peers, often using humor, analogies, or playful sketches to make abstract ideas more vivid. This quality carried into his professional life when he took up academic positions at Marischal College in Aberdeen, where he became a professor of natural philosophy at only 25 years old. Maxwell quickly established himself as a teacher who cared deeply about his students. He did not view teaching as a burden secondary to research, but as a central mission. His lectures were carefully prepared, filled with demonstrations, and delivered with a sense of enthusiasm that conveyed his own fascination with science. Though his style was sometimes idiosyncratic and his Scottish accent thick, students remembered the energy and sincerity that infused his teaching. Maxwell believed that the purpose of teaching science was not simply to pass on facts, but to cultivate habits of thought. He wanted students to grasp the logic of physical reasoning, to see how mathematics could illuminate the workings of the natural world, and to develop the confidence to explore on their own. He was patient with beginners, generous with his time, and willing to adapt his explanations to different levels of understanding. Stories from his students often recall how he would pause a lecture to answer a question thoroughly or repeat a point in several different ways until he felt the idea had truly been understood. At King's College London, where Maxwell moved in 1860, his reputation as a communicator grew further. There he taught not only advanced students but also a wider public, for London offered opportunities to engage with educated lay audiences curious about science. Maxwell did not shy away from this task. He welcomed the chance to bring scientific ideas to broader circles. His lectures were sprinkled with analogies drawn from everyday life, jokes that lightened the tone, and demonstrations that captured attention. He had a knack for showing that science was not a remote or forbidding subject, but something intimately connected with daily experience. Maxwell's skill as a communicator was not confined to the spoken word. He was also a prolific writer, and his writings reveal the same qualities of clarity, imagination, and accessibility. His treatise on electricity and magnetism, though dense by modern standards, was a masterwork of exposition for its time, systematically organizing the results of decades of research and presenting them in a coherent mathematical framework. To scientists of the late 19th century, it was a treasure chest of ideas and methods, a guidebook for further exploration. Beyond technical works, Maxwell also wrote essays, reviews, and popular pieces in which he reflected on the nature of science, the role of mathematics, and the relationship between scientific inquiry and human culture. In these writings, he demonstrated not only mastery of his subject, but also a gift for connecting science to broader intellectual and philosophical concerns. Maxwell's personality as a teacher was marked by humility and humor. He did not set himself on a pedestal above his students or readers. Instead, he saw himself as a fellow inquirer, sharing discoveries and puzzles, inviting others into the adventure of exploration. His love of verse often found its way into his teaching, as he composed playful poems or rhymes that captured scientific ideas in memorable form. Though light-hearted on the surface, these poems reflected a deeper conviction that learning should engage both the intellect and the imagination. To Maxwell, science was not a dry accumulation of facts but a living pursuit, full of wonder, beauty, and even joy. Perhaps Maxwell's most lasting contribution as a communicator came in his later years at Cambridge, where he became the first Cavendish Professor of Physics and oversaw the creation of the Cavendish Laboratory. Here, his dual roles as teacher and institution builder came together. He designed the laboratory not as a private workshop, but as a place for students and researchers to work together, to learn from one another, and to advance knowledge collectively. His vision for the Cavendish Laboratory was grounded in the belief that science progressed best when ideas and methods were shared, tested, and communicated openly. Under his leadership, the laboratory became a model for modern scientific research and education, producing generations of scientists who carried Maxwell's spirit of inquiry into the future. Even in his administrative duties, Maxwell never lost sight of the importance of communication. He corresponded widely with other scientists, offering encouragement, advice, or constructive criticism. His letters reveal a mind always engaged, always eager to discuss ideas, whether profound or playful. He had the rare ability to converse on equal terms with both leading scientists and curious amateurs, never talking down to anyone but always lifting the level of discussion with his insights. Maxwell's role as a teacher and communicator of science is perhaps best appreciated when one considers the generations he influenced. His students and readers did not merely absorb facts from him, they absorbed an attitude toward science, a way of approaching problems with rigor, creativity, and openness. They learned that science was not about memorizing laws but about discovering connections, that mathematics was not an obstacle but a language of beauty, that questions were as important as answers. Through his teaching, Maxwell instilled in others the values that had guided his own life: curiosity, humility, and a deep sense of wonder at the intelligibility of the universe. In reflecting on Maxwell's legacy, one cannot separate his role as a communicator from his role as a scientist. His equations endure as symbols of unification, but his teaching ensured that those equations did not remain hidden symbols, but became part of the living knowledge of humanity. His writings continue to inspire not only physicists, but also anyone who values the pursuit of truth. His laboratory stands as a testament to his vision of science as a collective, communicative enterprise. His humor and poetry remind us that learning can be joyful, that teaching is not only about instruction, but about awakening delight. Maxwell's genius as a scientist was matched by his generosity as a teacher and his clarity as a communicator. Together, these qualities ensured that his ideas did not fade into obscurity but spread widely, influencing both the scientific community and the wider culture. In him we see the model of a scientist who was not only a discoverer of truths, but also a guide, a mentor, and a storyteller. His legacy is therefore not only in the equations that bear his name, but in the countless minds he touched, minds that he helped to awaken to the beauty and unity of the natural world. James Clerk Maxwell's influence on science did not end with his own discoveries. In many ways, it truly began there. His unification of electricity and magnetism through his famous equations created a new foundation on which later generations of physicists would build entire revolutions in thought. His work was not merely a brilliant conclusion to an old line of inquiry, but a new starting point for modern physics. Among those who drew inspiration from Maxwell was Albert Einstein, who later acknowledged that Maxwell's work had lit the path toward the theory of relativity. Without Maxwell, the physics of the 20th century and the technologies that grew from it would have looked unimaginably different. To appreciate Maxwell's influence, it is important to recall what he achieved in the 1860s. By combining Faraday's experimental insights with mathematical rigor, Maxwell created a system of equations that described how electric and magnetic fields interact and propagate. These equations revealed that changes in electric fields produce magnetic fields, and changes in magnetic fields produce electric fields, so that the two are locked in an eternal dance. From this interdependence arose the concept of electromagnetic waves, moving through space at a fixed speed. When Maxwell calculated that this speed matched the measured speed of light, he boldly concluded that light itself was an electromagnetic wave. In a single stroke, he united optics, electricity, and magnetism into one coherent framework. This vision transformed physics. For centuries, light had been a puzzle, debated as either a wave or a stream of particles. Maxwell's equations gave the wave theory of light a profound theoretical basis, while also opening the door to the discovery of entire regions of the electromagnetic spectrum beyond visible light. His predictions were soon confirmed by Heinrich Hertz, who generated and detected radio waves in the 1880s, providing experimental proof of Maxwell's theory. The age of wireless communication began, leading eventually to radio, television, radar, and modern telecommunications. Every such technology traces its lineage directly to Maxwell's equations. Yet Maxwell's influence went far beyond practical invention. His equations reshaped the very concepts of space and time. According to classical Newtonian mechanics, there was no reason why the speed of light should be constant in all frames of reference. But Maxwell's theory implied precisely that, no matter how fast an observer moves, light should always travel at the same speed. This strange implication troubled physicists in the late 19th century, as it seemed to contradict the common-sense view of relative motion. The puzzle lingered until Albert Einstein, in 1905, resolved it by formulating the special theory of relativity. Einstein declared that space and time themselves must adjust so that the speed of light remains constant. In doing so, he elevated Maxwell's equations to a new status, making them central not only to electromagnetism, but to the very structure of the universe. Einstein himself admitted the depth of Maxwell's influence. He once remarked that the work of Maxwell was the most profound and fruitful change in physics since the time of Newton. For Einstein, Maxwell provided not just equations but a vision of unity, a demonstration that nature's forces could be described by elegant laws linking seemingly separate phenomena. This vision inspired Einstein's lifelong quest for further unification, leading to the general theory of relativity and his search for a unified field theory. In this way, Maxwell's legacy lived on in Einstein's work and through Einstein in the broader transformation of modern physics. Maxwell's influence can also be seen in quantum mechanics. Though he did not live to witness the quantum revolution, his electromagnetic theory provided the stage on which it unfolded. The interaction of light with matter, the quantization of electromagnetic energy into photons, and the development of quantum electrodynamics all grew from Maxwell's foundation. Richard Feynman, one of the architects of quantum electrodynamics in the 20th century, once observed that Maxwell's equations still form the starting point for our most advanced theories of light and matter. Every photon detected in a laboratory, every laser beam, every fiber optic cable operates according to principles that Maxwell first set down. The technological impact of Maxwell's ideas is impossible to overstate. Entire industries owe their existence to the electromagnetic theory he created. The generation, transmission, and distribution of electrical power, the operation of motors and generators, the use of electromagnetic radiation in medicine, the development of computers and digital communications, all these rest on principles encoded in Maxwell's equations. The modern world, lit by electric light and connected by wireless signals, is a world made possible by Maxwell's vision. But Maxwell's influence was not only intellectual or technological, it was also cultural. His work changed how humanity sees itself in relation to the cosmos. By showing that light is an electromagnetic phenomenon, Maxwell revealed a hidden unity underlying the diversity of natural phenomena. His equations suggested that nature was governed not by arbitrary rules, but by deep, elegant laws. This message resonated far beyond physics, inspiring thinkers in philosophy, mathematics, and even art. The idea that unseen forces connected all things, invisible yet lawful, shaped the cultural imagination of the modern age. Even today, Maxwell's equations remain central to physics education worldwide. They are taught not only as practical tools, but as exemplars of scientific beauty. Students encounter them as a moment of revelation, the point at which electricity, magnetism, and light cease to be separate subjects and merge into one harmonious whole. For many, this encounter mirrors the intellectual journey of Einstein and others who found in Maxwell's work the spark of inspiration for their own breakthroughs. Maxwell's relatively short life makes his legacy all the more remarkable. He died in 1879 at the age of 48, the very year Einstein was born. It is tempting to imagine this as a symbolic passing of the torch, as if the visionary who had unified electricity and magnetism handed the next stage of discovery to the man who would unify space and time. The connection between the two is not mere coincidence, but a genuine lineage of ideas. Einstein carried Maxwell's insights into a new century, and through him, Maxwell's spirit of unification has continued to shape science ever since. When we look at the history of physics, we see a chain of giants, each building upon the last. Newton gave the world the laws of motion and gravitation, which governed mechanics for centuries. Maxwell extended the reach of law to electricity and magnetism, forging a new unity. Einstein, inspired by Maxwell, reshaped our understanding of space and time. And later, quantum theory extended this unifying vision to the subatomic realm. In this lineage, Maxwell stands as the bridge between classical and modern physics, the mind who transformed electricity and magnetism from curiosities into the central framework of science. The influence of James Clerk Maxwell is therefore not confined to the past. It continues to live in every device powered by electricity, in every radio wave crossing the atmosphere, in every beam of light that carries information through a fiber optic cable, and in every scientific theory that seeks to describe the universe. His legacy is written not only in the equations that bear his name, but in the very structure of modern life and thought. To understand the world today is to recognize the enduring impact of Maxwell's vision. He was not only the unifier of electricity and magnetism, but also the inspiration for Einstein and the architect of the scientific age that followed. James Clerk Maxwell's name belongs to a rare circle of thinkers whose ideas did not merely solve problems of their age, but redefined the trajectory of human knowledge. His legacy is not just that of a brilliant physicist who unified electricity and magnetism, but of a visionary whose insights transformed science and laid the foundations of the modern technological world. To speak of Maxwell is to speak of continuity, of a mind that bridged past traditions with future revolutions, and of a legacy that still reverberates in every scientific discovery and invention we depend upon today. When Maxwell produced his equations in the mid-19th century, he provided more than a new theory of electromagnetism. He gave humanity a universal language to describe forces that shape the cosmos. His four equations, elegant and concise, became the DNA of modern physics. They provided a foundation upon which Einstein constructed relativity, and upon which quantum mechanics found its footing. Maxwell's vision was not limited to electricity and magnetism. It was a vision of unity itself, of finding harmony in the seeming diversity of natural forces. In this sense, his legacy can be compared only with Isaac Newton, whose laws of motion and gravity reshaped science centuries earlier. Newton explained the heavens above and the motion of earthly bodies. Maxwell revealed the invisible fabric of fields that linked light, electricity, and magnetism into one. But Maxwell's influence stretches beyond the rarefied world of theory. His equations created the intellectual scaffolding for inventions that have become inseparable from modern civilization. Every time an electric current powers a home, every time a signal is transmitted wirelessly across continents, every time information travels at the speed of light through fiber optics, the hand of Maxwell is present. His theoretical prediction that electromagnetic waves exist beyond visible light opened the door to discoveries of radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays, each of which became a foundation for new technologies. The global communication networks of the 21st century, the medical imaging devices that probe inside the human body, the satellites that orbit the Earth, and the very electrical infrastructure of modern life all stem from Maxwell's vision. He never lived to see these developments, yet his legacy shaped them all. Maxwell's work in optics and color vision also left a permanent mark. His experiments on how the human eye perceives color helped establish the basis of color photography. In 1861, he produced the first color photograph by combining three separate filtered images. What seemed like a curiosity in his day later became the foundation of photography, cinema, and digital imaging. The vibrant images that define modern culture, from art to entertainment to communication, trace their ancestry to the insight of a 19th-century Scottish physicist who wanted to understand how the eye and light interact. His curiosity about perception foreshadowed the blending of science and technology with art, a legacy that continues in today's world of visual media. Maxwell's contributions to the kinetic theory of gases also built a bridge to statistical mechanics, a cornerstone of modern thermodynamics. His insights on molecular motion and distribution prepared the way for Ludwig Boltzmann and others to develop statistical physics. In this area, too, Maxwell left behind not only equations but a method, a way of thinking about complex systems through probability and mathematics. His legacy here continues to shape disciplines as diverse as chemistry, material science, meteorology, and even economics. The fingerprints of Maxwell's intellectual versatility extend far beyond the boundaries of what we normally call physics. One cannot speak of Maxwell's legacy without mentioning his role in shaping the institutions of science. At Cambridge, he oversaw the founding of the Cavendish Laboratory, which would later become the birthplace of some of the most important discoveries of modern physics, including the structure of DNA, the neutron, and advances in nuclear and solid-state physics. By envisioning a place where students could experiment, collaborate, and learn, Maxwell created not only a building but a culture of research that carried his spirit into generations he would never meet. The Cavendish became a temple of science and Maxwell its first architect. Maxwell's legacy is also one of inspiration. His ability to connect mathematics with physical reality set a standard for how modern science approaches problems. Later physicists, from Einstein to Feynman, saw in Maxwell an example of how abstract thought and experimental observation could be woven into a single tapestry. Einstein himself admitted that his work on relativity was inspired by the implications of Maxwell's theory, and Feynman often noted that Maxwell's equations were the most profound set of laws in physics. To inspire such minds is itself a measure of legacy. Perhaps most remarkable is the way Maxwell transformed how humanity sees the universe. Before him, electricity and magnetism were curiosities, the subject of experiments with sparks and compasses. After him, they were revealed as universal forces, woven into the very light that illuminates the world. His equations suggested that nature was not a patchwork of disconnected laws, but a coherent unity. This vision of unity has become the guiding star of modern physics, inspiring the search for deeper connections among the fundamental forces, from the electroweak unification to the ongoing quest for a grand unified theory. In this way, Maxwell's legacy is alive not only in what we know but in what we continue to seek. His personal qualities also shaped his legacy. Maxwell was known for his humility, his humor, and his ability to see beauty in both mathematics and nature. Unlike some scientific figures whose ambition was fueled by rivalry or ego, Maxwell approached science as a joyful act of discovery. His playful poems, his willingness to teach patiently, and his vision for institutions like the Cavendish all reflect a man who understood that science was a human endeavor, meant to be shared, nurtured, and passed on. His legacy is thus not only intellectual but cultural, reminding us that great science grows in an atmosphere of curiosity, generosity, and imagination. In the final measure, James Clerk Maxwell's legacy is everywhere. It is in the theories that describe the universe, in the technologies that power our civilization, in the laboratories that educate new generations, and in the very way scientists think about unity and beauty in nature. Few figures in history have left such a pervasive and enduring mark. Maxwell died in 1879 at the age of only 48, but in those short years he transformed the course of human thought. His legacy is not a relic of the past, but a living presence, woven into the electricity that lights cities, the signals that connect continents, the images that capture memories, and the equations that continue to inspire discovery. He was and remains a visionary who transformed science and technology, a figure whose influence endures as long as humanity seeks to understand the world and harness its forces.